Now, the topic that is Kirchhoff's rules. Kirchhoff's rules are very useful for the circuit analysis. It implies that Kirchhoff's rules are very useful to find the potential differences across the components connected in the network, as well as with the help of Kirchhoff's rules, one can find the current flowing through different branches of the network. Network means the complex connections of components like resistors, cells. So that is complex combination of these components, means maybe in series, in parallel, and sometime mixed mode connection. Now, there are two rules suggested by scientist Kirchhoff. One that is known as junction rule and another one that is known as loop rule. Junction rule suggests this thing: at any junction in the given network, the sum of the currents entering to the junction, that is equal to the sum of the currents leaving the junction. Actually, this junction rule, that is the consequence of law of conservation of electric charge. Now see here, as per law of conservation of electric charge, we know this thing: at any point, charge will not be accumulated, charge will not be destroyed, and new charge that will not be produced. So here the current is constituted due to flow of charges. So this same junction rule that we can represent like this: the total amount of charge entering the junction, that is equal to the total amount of charge leaving the junction per unit time. So this one is the consequence of law of conservation of electric charge. Then second one. Then after loop rule. Loop rule suggests this thing: the algebraic sum of the changes in the potential differences around any closed loop involving resistors and cells in the loop, that is equal to 0. Actually, this loop rule, that is the consequence of law of conservation of energy. After all, the potential, that is nothing but energy, and the potential difference, that is the change in energy. So in the closed loop, if we take the algebraic summation of the changes in the potential differences across each component, it implies that we are taking the change in energy of the unit positive charge when it is moving from one end to other end of the component. Then that change in energy that we take here. So when resultantly the summation comes to 0, it implies that the energy is conserved. એટલે કે યુનિટ પોઝિટિવ ચાર્જ એક એન્ડ થી બીજા એન્ડ ઉપર ગયો કોઈ કોમ્પોનન્ટમાં, and suppose its energy decreases. પછી બીજા કોમ્પોનન્ટમાં suppose one end to other end એ move થયો, and suppose its energy increases. So in this way, if we take the algebraic summation of the change in potential differences, or in other words we can say energies, and finally if we get 0, it implies that the energy of that unit positive charge remains constant one. Okay, so this is the loop rule. Clear up to this one? Let's understand these two rules with example. Suppose, as shown in the figure, we have a network in which some resistors and cells are connected as shown in the figure. Now, first of all, we have to understand the junction and the loop for given network. Which point in the network that is called junction? So the point or the terminal in the network where more than two components of the circuit are connected, that is known as junction. And when a closed circuit is formed by connecting the components, then it is known as loop. Now see here, this particular network given to you. So in this particular network, there are two junctions. One junction that is A and second one that is D. Because see, at A, this 30 ohm resistor is connected, this 40 ohm resistor is connected, and this 80 volt battery is connected. So more than two components are connected. Similarly, at D also more than two components are connected. So in this particular circuit, terminal A, or we can say point A and D are the junctions. Clear to all of you? Now, how many loops are there in this particular network? So loop means a closed circuit in which the components are connected. So here total 3 loops are there. See, A, B, C, D, A. This is one loop. Second one that is A, D, E, F, A. And third one that is this outer one. A, B, C, D, E, F, A. So total 3 loops are there in this particular network. So now the concept of junction and loop is clear to all of you. Now as per Kirchhoff's junction rule, we can write here, say, consider the junction A. So for junction A, see the total amount of current entering the junction, that is I3. Only one current is entering to junction A. But two currents, I1 and I2, these two currents are leaving the junction. So we can write as per Kirchhoff's junction rule, I3 that is equal to I1 plus I2. This is the junction rule. Clear to all of you? Now here, to understand the loop rule, consider the loop A, B, C, D, A. Okay? Now, start from A. Now we are moving from A to B, then after B to C, then after C to D, then after D to A. So loop will be completed. So A to B, there is no component, so no potential difference. Then B to C. Now current I1 is flowing through this 30 ohm resistance. Now when through this 30 ohm resistance I1 current is flowing, then between two terminal of this 30 ohm resistor, the potential difference as per Ohm's law, we can write V equal to IR. So potential difference, that is 30 I1. So here it is 30 I1, that is the potential difference between 30 ohm resistor. Okay. Later on we will discuss about these positive negative signs. Then after, when we move from C to D, there is no component, so no potential drop. Then after we move from D to A, so here is the battery of 45 volt. So potential difference between two terminal of the battery, that is 45 volt. So here 45 is taken. Then after, see the current I3 is flowing through 1 ohm resistor. So potential difference across 1 ohm resistor, that is 1 I3. Then after, I3 current is flowing through 40 ohm resistor. So potential difference, that is 40 I3. Now, here we have to take the algebraic summation of all these potential differences which we calculated in this loop. Now see here, first think about this 30 ohm resistor. Now we know this thing, current always flows from high potential to low potential. So through 30 ohm resistor, the current is flowing from left to right. So this left terminal of 30 ohm resistor, that we can say is at higher potential, and this right side terminal of 30 ohm resistor, that we can say is at lower potential. Now when we move from B to C, then first high potential terminal is there, and then after low potential terminal is there. When we take the potential difference, difference means final minus initial. So for first terminal, initial potential, that is high potential. For this second terminal, which is final terminal, for that the final potential is low potential. So final minus initial potential, so here you will get answer negative. So negative sign is introduced here. Clear up to this one? Then after, when we move from D to A, so at that time, first negative terminal appears here. Then after, positive terminal of the battery. Negative terminal of the battery is at lower potential. Positive terminal, that is at higher potential. So if we take here final minus initial, so this will come to positive. So here 45 volt potential difference, that is taken as positive. Now here, simply remember one thing. See, for this 30 ohm resistor, we consider the potential difference, that is minus 30 I1. હવે શોર્ટકટ મેથડ યાદ રાખજો અહીંયા કે જો current is flowing from B to C and you are also moving from B to C. So when you are moving through the resistor in the direction of current, then always take the potential difference across that resistor is negative. તો હવે એના કરતા ઊંધું, if you are moving in the opposite direction of the current flowing through the resistor, then take the potential difference across it as positive. હવે બેટરી માટે શોર્ટકટ યાદ રાખજો કે through the battery, when you are moving from negative terminal to positive terminal, then take the potential difference of battery positive. હવે એના કરતા ઊંધું, if you are moving through the battery from positive terminal to negative terminal of the battery, then take the potential difference negative. So now see, when you are moving from D to A, so through 1 ohm resistor, you are moving in the direction of the current, because direction of the current is the same one. So 1I3, that potential difference you have to take negative. Again, through 40 ohm resistor, you are moving in the direction of the current. See, direction of the current, that is B to A, and you are also moving B to A. So potential difference across 40 ohm, that is taken here negative, so minus 40I3, and now this algebraic summation of the potential differences, that is equal to 0 in this loop. This is loop rule. Clear to all of you? Now consider the loop A, D, E, F, A. So when you are moving from A to D, now see, when you are moving A to D, so through the resistor 40 ohm, the current, that is in the opposite direction, then your considered path. So take the potential difference 40I3 across this 40 ohm resistor, that is positive. Again, through 1 ohm resistor, you are moving in the opposite direction of the current. So again, take the potential difference 1I3 positive. Then through this battery, you are moving from positive terminal to negative terminal of the battery. So potential difference that you have to take negative, minus 45. Then after D to E, when you are moving, so 20 ohm resistor is there, and through this 20 ohm resistor, this I2 current is flowing from E to D. So you are moving D to E, current is flowing from E to D. So you are moving in the opposite direction of current. So again the potential difference 20 I2, that is taken positive. Then E to F. So you are moving through this 1 ohm resistor in the opposite direction of this current. So again the potential difference 1 I2, that is taken positive. Then through this 80 volt battery, you are moving from positive terminal to negative terminal. So you have to take that potential difference minus 80, and this is equal to 0. So in this way, the second rule that we can apply to the loop. Clear to all of you? Example 3.6. A battery of 10 volt and negligible internal resistance is connected across the diagonally opposite corners of a cubical network consisting of 12 resistors, each of resistance 1 ohm. Figure. Determine the equivalent resistance of the network and the current along each edge of the cube. Now, see, this particular circuit is given to you, and you have to find the equivalent resistance of the network between terminal A and this diagonally opposite point, this one. Okay, and then we have to find the current along each edge of the cube. This is our problem. Clear problem? Now the network is given to you as shown in the figure. The cube of the resistance is connected in each edge of the cube, that is given to you. And now we want to find the equivalent resistance of this network between two diagonally opposite points. So here in our case, we can say we want to find the equivalent or resultant resistance between terminal A and H. Therefore, between A and H, the battery connected of 10 volt is given to you. Now suppose battery supply 6I current to the network. Here you can take 3I current also, you can take I current also. આપણને જો બિલકુલ જજમેન્ટ ના આવે કે આગળ જતા ડિસ્ટ્રીબ્યુશન ઓફ કરન્ટ્સ કેવી રીતે થવાનું છે તો સિમ્પલી I લઈ લો તો પણ ચાલે. ઓકે, નાઉ સી here in junction A 6I current enters. Now the current will leave this network from which terminal? From H. H માંથી આ બધો કરંટ બહાર આવીને ફરી પાછો બેટરીમાં જતો રહેશે. Now here consider the shortest path in the network from A to H. So if you consider any path, but that should be the shortest one. So see here, now I am considering different paths, A, B, then B to C, C to H, or A to B, B to G, G to H, or A to D, D to C, C to H, or A to D, D to E, E to H, then A to F, F to E to H, or A to F, F to G to H. તો એમાંથી તમારો 6I કરંટ આ ત્રણ ડાયરેક્શનની અંદર જ્યારે ડિસ્ટ્રીબ્યુટ થશે તો ત્યાંથી એને H સુધી પહોંચવામાં સેમ રેઝિસ્ટન્સ ઓફર થશે, કારણ કે કોઈ પણ શોર્ટેસ્ટ પાથ તમે ચૂઝ કરો તો એ પાથમાં 3 રેઝિસ્ટર્સ એપિયર થાય છે. So now you can say logically this thing, this 6I current when enter to junction A and then after it is divided in 3 parts when it leave the junction A, so at that time it will be equally distributed in all the 3 branches as current 2I, current 2I, current 2I in the branches A to B, A to D and A to F. Clear to all of you? Now when this 2I current A to B enter to junction B, and then after when it leave junction B, then it will be divided in 2 parts, but B to C and C to H as well as B to G and G to H, on both the paths 2 resistors appears in the path. It implies that both the paths are identical one, same resistances are offered. It implies that this 2I current entering to junction B will be equally distributed in 2 branches B to C and B to G when it leave junction B. Clear to all of you? Similarly, when A to D, these 2I current enter to junction D, and when it leave junction D, then again the current will be equally distributed in the branch D to C, that is I, and D to E, that is also I. Then after, the current 2I in the branch A to F, when it enter to junction F, and then after when it leave junction F again, it will be distributed in two equal parts, current I in the branch F to G and current I in the branch F to E. Clear to all of you? Now here, suppose we think about junction C, then D to C and B to C, I current, resultantly 2I current enter to junction C, and when it leave C, so in the branch C to H, we will get 2I current. Similarly, I current enter to junction G. So when it leave junction G, then in the branch G to H, again the current will be 2I. Then after, current enter to junction E, that is I. So when it leave the junction E, 2I current will be there in the branch E to H. So from these three branches, EH, GH and CH, 2I current enter to this junction H. So when it leave the junction H, total current 6I reach to the battery. Which one was the circuit current? Clear to all of you? Now here, using Kirchhoff's first rule, the distribution of current is made in different branches. Now let's use Kirchhoff's loop rule. So here you can consider any loop. Arbitrarily you can consider any loop. Okay? Provided that you have to take battery within the loop. Here we consider the loop A, B, C, H, then E to A. Loop is completed. A, B, C, H, E, A. Start from A. So 2I current is flowing through resistor R in the direction A to B, and you are also moving in the direction A to B. The potential difference, that is minus 2IR. Then B to C, current through the resistor R, that is I, and we are moving in the direction of the current, so potential difference, that is minus IR. Then after C to H, so current through resistor R, that is 2I, and we are moving in the direction of the current C to H. So again the potential difference, that is minus 2IR. Then H to E to A. So you are moving through the battery from negative terminal to positive terminal. So potential difference across that battery, that is plus E, and finally when you reach at A, we can write that is equal to 0. Now clear this algebraic summation of the potential differences. Now here minus 2IR minus IR minus 2IR, that is resultantly minus 5IR, take it on right hand side, so we can write E equal to 5IR. Say this is the equation number 1. Now suppose the equivalent resistance of the network between A and H, that is capital R. We already discussed this thing. Equivalent resistance of any combination or connection means if that entire combination is replaced by that resistor R, then the same battery will constitute the same current in the circuit. Then we can say that is the equivalent resistance. So here, if we say R, that is the equivalent resistance between A and H, it implies that if we replace this entire network by only one resistor R between A and H, then the same battery will constitute the same current in the circuit. So we can write for equivalent resistance R, that is E equal to 6IR. Now compare the equation number 1 and 2. So 6IR equal to 5IR. So equivalent resistance of the network between these two diagonally opposite points R, that is 5 by 6 small r. But the value of small r, that is given to you 1 ohm. So we can write the equivalent resistance R, that is equal to 5 by 6 ohm. Clear to all of you up to this one? Now, from this equation number 1, we can write I, that is equal to E upon 5R. So E, that is 10, 5, R, that is 1. So your I comes to 2 ampere. Now, battery supplies 6I current that we considered. I, we calculated 2 ampere. It implies that now we can say battery is supplying 12 ampere current. Now all these blue answers. So A to B, the current is 2I, means it is 4 ampere. B to C, current is I, means 2 ampere. In this way, you can represent currents through each edge of the cube. Clear to all of you? Example 3.7. Determine the current in each branch of the network shown in figure. Now network is given to you, the components connected. Their values are given to you as well as the currents in each branch, that is also given to you. Now see, this one is your network and you have to find the current through each branch. Now here the total number of currents which are unknown are given to you, I1, I2 and I3. So easily you can understand when 3 unknown currents you want to find, it implies that you have to prepare 3 equations. It implies that you have to consider here 3 loops. Now let's start. Suppose first we consider loop A, B, C, A. So A to B, current is I2 through resistor 4 ohm. We are moving in the direction of the current. So here the potential difference is taken minus 4I2. Then after B to C, so 2 ohm resistor current through it, that is given to you I2 plus I3. And we are moving in the direction of the current. So the potential difference 2 into I2 plus I3, that is taken negative. So minus 2 I2 plus I3. Then after C to A, so through resistor 1 ohm, you are moving in the direction of current I1. So potential difference minus 1 I1, and through the battery you are moving from negative to positive terminal of the battery. So plus 10, that is equal to 0. Now simplify this one and prepare the current in terms of I1, I2, I3. Clear? Now consider another loop A, C, D, A. So A to C, you are moving through this battery from positive terminal to negative terminal, so minus 10. Then through resistor 1 ohm, you are moving in the opposite direction of current I1. So potential difference plus 1 I1. Then C to D, you are moving in the direction of the current I2 plus I3 minus I1 through resistor 2 ohm. So potential difference here minus 2 I2 plus I3 minus I1, this one. Then after D to A, you are moving in the opposite direction of the current I1 minus I2 through resistor 4 ohm. So potential difference plus 4 into I1 minus I2, that is equal to 0. Again simplify this one and prepare the equation in terms of I1, I2 and I3. Say this is equation number 2. Now consider third loop, that is B, C, D, E, B. So B to C, you are moving in the direction of the current I2 plus I3 through 2 ohm resistor. So minus 2 into I2 plus I3, the potential difference is taken. Then C to D, you are moving in the direction of the current I2 plus I3 minus I1 through resistor 2 ohm. So again the potential difference, that is negative, minus 2 into I2 plus I3 minus I1. Then D to E to B. So you are moving from negative terminal to positive terminal of the battery. So potential difference is taken plus 5 volt and resultant, that is 0 when you reach at B. Again simplify this equation and prepare the equation in terms of I1, I2, I3. Say this is equation number 3. Now we have 3 equations and 3 unknown currents I1, I2, I3. Now you all are aware about elimination method. So by using elimination method, you have to find I1, I2, I3. અહીંયા મેં એ કર્યું નથી, એ તમે જાતે કરજો. And finally you will get I1, that is 2.5 ampere, I2 that is 5 by 8 ampere, I3 that is 15 by 8 ampere. Now current through each branch. So see, suppose we take a current in AD branch. So that is I1 minus I2. So current I in AD branch, that is I1 minus I2. So that is 2.5 minus 5 by 8. And now whatever is your answer. So in this manner you have to write current through each branch of the network. Clear to all of you? Next topic, that is Wheatstone bridge. Wheatstone bridge, that is the circuit with the help of which one can find the unknown resistance. Okay, so first we have to understand theoretically the circuit of the Wheatstone bridge, and then after we will discuss the experimental circuit which we use in laboratory. Now see, in Wheatstone bridge circuit, a loop is formed by connecting 4 resistors as shown in this figure. A to B one resistor, B to C another resistor, C to D the third one, and D to A fourth one. So using 4 resistor here, a loop is formed. Then after, between two diagonally opposite points, here between B and D, a galvanometer is connected, and between two remaining diagonally opposite points, battery is connected. So this particular circuit prepared in this way, that is known as Wheatstone bridge circuit. Now using this particular circuit, one can find the unknown resistance. Say, out of these 4 resistances, R1, R2, R3, R4, suppose we take R4, that is an unknown resistance. Now here, suppose battery supply total I current to the circuit. Now here we have to adjust the values of these resistances R1, R2 and R3 such that the current in this particular branch B to D, that is 0. It implies that galvanometer shows you 0 deflection. When galvanometer shows you 0 deflection, then we can say bridge is balanced. Or in other words, we can say when the bridge is balanced, always galvanometer shows you 0 deflection. So here we have to adjust the values of the resistances R1, R2 and R3 such that the galvanometer shows you 0 deflection. So current through galvanometer is 0 and we can say bridge is balanced. So here when the current I enter to this junction A, now suppose it is divided in two parts, I1 in branch AD and I2 in branch AB. Now B2D or D2A, D2B, there is no current. So this I2 from B, it will flow to C. Similarly, current I1 A to D, now that will flow from D to C. And when in C current I1, I2 enter, then resultant leaving, that is I1 plus I2, that is again equal to I. Now here suppose we consider the loop A, B, D, A. So A to B, we are moving in the direction of the current I2 through resistor R2. So the potential difference, that is minus I2 R2. Then B to D, B to D in that particular branch, there is no current. So potential difference is 0 in that branch. Now D to A, you are moving in the opposite direction of current I1 through resistor R1. So potential difference I1 R1, that is taken positive, that is equal to 0. So we can write I1 R1 equal to I2 R2. Therefore I1 upon I2, that is R2 upon R1. Say this is equation number 1. Now consider second loop, that is B, C, D, B. So when you are moving B to C, you are moving in the direction of the current I2 through resistor R4, which is a known one. So the potential difference, that is minus I2 R4. Then C2D, you are moving in the opposite direction of the current I1 through resistor R3. So the potential difference, that is plus I1 R3. Then D2B, there is no current, so no potential difference. So when you reach at B, resultant is 0. So you can write I1 R3 equal to I2 R4. So you can write now I1 upon I2, that is equal to R4 upon R3. Clear to all of you up to this? Now compare equation number 1 and 2. So we can write R2 by R1, that is equal to R4 by R3. So here we can say when this happens, the bridge is balanced. Because when we considered there is no current through the galvanometer, we derived this identity. So we can say this one is the condition to balance the bridge. If this condition is satisfied, definitely the bridge will be balanced and there will be no current through the galvanometer. Now here make R4 as a subject of equation. So R4, that is equal to R3 into R2 upon R1. Now R1, R2, R3, all these three resistances are known resistances and R4 was unknown. So using Wheatstone bridge circuit, one can find the unknown resistance. Clear to all of you? Meter bridge. Meter bridge itself is Wheatstone bridge. And this one is now experimental, or we can say laboratory circuit. Why this one is known as meter bridge? Because here the wire which we use in this circuit, that we take of length 100 centimeter, or we can say 1 meter, and therefore this is known as meter bridge. In meter bridge, this red represented here are the copper strips. This one straight one and these two L-shaped. And here, as shown in the figure, two gaps are kept and this entire arrangement that is mounted on the wooden plank. And between this terminal A and C, a wire having length 1 meter, having uniform cross-sectional area, that is connected. Now see, in one gap we connect the resistor R. So in theory, we used 4 resistors. So this resistor R will behave as resistor R2 connected in the circuit, theoretical circuit. This resistance connected in second gap of the meter bridge S, that behave as resistance R4. Now here galvanometer is connected between this terminal B and another terminal of the galvanometer is connected with jockey key. And between A and C, battery is connected. Now here we have to place the jockey key at such a position so that galvanometer shows you 0 deflection. So suppose at point D, when the key is placed, we are getting 0 deflection in the galvanometer. So we can say bridge is now balanced. So at that time, the length of this wire A to D, which one is represented here as L1. So whatever is the resistance of this L1 length of the wire, that will behave as resistance R1, and whatever is the resistance of the remaining part of the wire, that will behave as resistance R3. Now, suppose resistance per unit length of the wire, or we can say per centimeter length, that is RCM. Now, resistance of AD part, that is with length L1. So per centimeter, if resistance is RCM, so for length L1, resistance is how much? So resistance of AD part of the wire, that is L1 into RCM, and resistance of DC part of the wire, that is length L2, so L2 into RCM. Now, when the bridge is balanced, R, this resistance upon resistance of AD part, that is equal to resistance S upon resistance of DC part. So we can write resistance R, that is equal to RAD upon RDC into S. Replace RAD by L1 RCM, replace RDC by L2 RCM into S as it is. RCM cancelled. So finally we can write R equal to L1 upon L2 into S. Or you can write R, that is L1. Now total length of the wire is 100 centimeters. So you can write L2, that is 100 minus L1 into S. And using this equation, and by measuring the length for the null point, when galvanometer shows zero deflection, the point obtained, that is also known as null point. So find out the length of the wire for null point and then calculate the unknown resistance. Clear to all of you?